Okay. Because the show is called I Love Lucy. Ooh. Now I can't tell if you're joking or not. Okay, so to get started, what I want you to do is I want you to decide. So I really like these questions because I think they're really interesting because I think I like watching these videos. But which of these following do you think will win in a drag race? We have an F-16 fighter jet, we have a Formula One car, a motorcycle, a Tesla Model S, and an Aston Martin Vantage. So which one out of these five would you think would win in a drag race? They actually did race all of these at once, and they even raced a couple more cars as well at the same time. Unfortunately, I didn't put them in there, but which of the following do you think will win in a drag race? I should have put a Toyota Prius in there too. Yo, what up, fam? What is up? Uh, because let's say the same thing every time. So usually say the sky is up, but that's kind of lame. So, what's up? What's up, home slice? What up, dog? What's up, dog? Okay, yeah. So which of the following do you think would win in a drag race? A fighter jet, a Formula One car, an Aston Martin Vantage. What? The Jeep Wrangler? So would you say is that it's a very it's, let's just say let's just say you fit the demographic of a Jeep Wrangler. You a Jeep Wrangler too? Yeah, so you fit the demographic too. Yeah, that's my polite way of saying that's very basic, but okay, so take one more minute for people to vote. What do you think will win? So we have a very strong tie between the fighter jet and the Formula One car. 7 people said the fighter jet, 7 people said the Formula One car, and then we have a couple other votes spread out. Really, really, really interesting. I really think these are really interesting. Oh, the Formula One car looks like it broke away. It has 8 out of 8 votes compared to 7. Take so what I'm going to do is now is we're going to actually watch the video of who actually wins. It's a pretty gnarly video actually. Um, So what's a drag race? It's just like you line up all the things at once, and then it's like they line up all the things at once, and then they like just say go. Well, they wave the flag and then they say go, and then they like race to a certain line. Yeah. But it's like it starts on the ground. Yeah, because after a certain point, the plane will take off because it has enough lift in its wings. People drag race at let's just say, which is people do drag race quite a bit in certain areas at certain times in the day. Yes, I am very specific. Okay, so from personal experience, yeah, definitely, I'm definitely. Oh, that's even worse. I wasn't talking about here. I wasn't even talking about LA. Can't relate. Can't relate to that. Okay, so we're gonna watch. Oh, there's a private jet here too. I totally forgot. There's a private jet in this race. There's actually a Lotus, and there's like another car in here. There's actually a lot of cars in this race. Oh, that's a tricked out Tesla. That's pretty sick. Pretty gnarly. Yeah, so they're all starting on the ground. They're all starting at the same line, and then you're gonna start, and then they're gonna try to, and then the finish is just also one line. So they're gonna see who reaches the finish first. Or you also get to see some points of view of the different people racing it. I think the fighter group is starting to take off, I think. All righty. Okay, so it looks like if you look at the finish line here, it looks like the motorcycle wins, followed by the F1 car, and then followed by the fighter jet. And then the rest of them, they're so far behind. We don't care about them at all. So this is what happens when you have a lot of money and a lot of toys. You can do stuff like this. So what I want you to do is I want you to try to come up with an explanation as to why the motorcycle won. Because nobody picked the motorcycle. Not a single, so out of 17 people, not a single person picked the motorcycle. I think statistically, if we were to just take if everyone were just to guess randomly, you actually would have done better than what we have right here. So 0 out of 7 people picked the motorcycle. So what I want you to do now is I want you to try to come up with an explanation as to why the motorcycle won, because clearly it was not intuitive at all. So I want you to try to come up with an explanation as to why the motorcycle won. I'm going to put you in your groups. Let's see if you guys can come up with an explanation for this. I have to like go into it to like change it. So it's like, it's a whole thing. It's like, it takes more than like 5 seconds. I wasn't apologizing. Uh, yeah, I wasn't apologizing. I don't apologize for things. Okay, so here's what we're gonna do. So what I'm going to do is I'm going to arrange these cars and objects from lightest to heaviest. Okay, so I'm going to arrange these things from lightest to heaviest. And let's see if we can come up with a relationship between the mass and the acceleration. So the lightest, I think we can all agree, is a motorcycle. Motorcycle, I mean, it's by far the smallest, so I think we can all agree that the motorcycle is the lightest of those mass. The next one, I think, that's probably the lightest, is probably the cars, the Formula One car. The Formula One cars are also very light because they need to be very fast. But they're also very light. The next one we could probably say is, I think the next one we could probably say is like a Tesla or something. And then we could say something like, a supercar. Then we get something like that. Then we get something like yeah. So we're just going to basically give a rough hierarchy of weights. Now we're going to take a look at how fast are these objects. What place did we get? So the motorcycle was first place. That Ford car was second place. The Tesla, I think, was fourth. The supercar, I think, was probably fifth, I think. F-16 was third. And the fighter jet was like so this is sort of the data we have. In science, what we like to do is we like to construct trends. We like to look at trends and we like to try to construct relationships between objects. So what the quantities we're looking at here is the mass of an object and its acceleration. So how does the mass of an object affect its acceleration? So as you can look here, there's a general trend. The lighter the object is, it tends to go fast, right? The motorcycle is the fastest because it's the least mass. F1 car, second least mass. So the general trend here is that the lower the mass, the higher the acceleration. The reason why is because the lighter the mass of an object is, the less force it requires to make it move, right? So if I'm trying to make a truck move, I need a lot of force, whereas if I'm trying to make a motorcycle move, I don't need as much force. So these are three major quantities: mass, force, and acceleration. And there are relationships between them that we're going to take a look at today, with this being a good starting point for them. So the next thing we're going to look at is something called Newton's third law. So we're going to sort of backtrack a little bit. We're going to go back to the Earth's planetary motion. So last time what we talked about how the Earth pulls on us and we pull on the Earth. And it ends up being that the Earth pulls us with the same amount of force that we pull on the Earth. So when I asked you, okay, try to come up with a reason for this, it was very challenging because it doesn't make a lot of sense. However, the main reason why this works is this is also the same phenomenon that allows rockets to work. It's something called Newton's third law. So basically, what the idea is, for every force I exert, there is an equal and opposite force in the other direction. So if object A pushes against object B with a certain force, object B will exert a force on A with the same magnitude, but in the opposite direction. So basically, if I push on an object, the object pushes on me with the same amount of force, just in the opposite direction. So the Earth, so in other words, I'm pulling on the Earth with the same amount of force that the Earth is pulling on me, but they just are working in different directions. So that's sort of the basic idea behind why gravity works the way it is, why we are exerting the same force as the Earth exerts on us. But there's a lot of different kinds of these forces, and they're very, very, very present. So what I want you to do is I want you to try to come up with 3 examples of equal and opposite forces. We also call these action-reaction forces. So basically, when I do something, there's something that applies the same force to me. So I want you to see if you can come up with 3 examples of equal and opposite forces. Um, they're actually much more present than you would think, much more present. So once again, let's see if we can come up with some equal and opposite forces for this. Tyler, I'm moving you to Bryn's group because everyone in your group, I don't know what happened to them. You scared them all away. Okay, so what I want us to do now is I want us to what I'm going to I'm going to give you a minute or so, and in the chat I want you to so in a minute or so I want you to put in one example of an action reaction force, and then let's see how many different examples we can come up with. So I'm going to give you about a minute. So let's see, what time is it right now? It's 12:30, so we'll take until 12:32 to come up with an action reaction force. And at 12:32, I'll see it hit enter, and then we'll see how many we can get. All right, let's take, how much more time? Let's take 10 more seconds. 5, 4, 3, 2, 1. Hit enter. I want to see those ideas. Like, that's hilarious. That's really funny. Let's get some more. Let's get some more. I heard some really good ones. I heard some really good ones. Okay, so pushing a cart up a hill and coming back to you. Yeah, so when you're pushing a cart up a hill, the cart is also pushing back to you, pushing back on you. So anytime you're pushing on an object, and the object is also pushing back to you. So that's definitely a good example. Walking. So believe it or not, walking is probably one of the best examples, is because in order to walk, your foot is basically pushing on the ground, and then the ground is pushing back on you and allowing you to walk. So if yeah, so you have to have that contact with the ground in order to walk, right? If you were in air and you tried walking, it just wouldn't work because you wouldn't be able to push against anything. So that's a great example. Throwing a ball against the wall and watching it bounce back towards you. That's a great example. That's why wall ball works. Kicking a soccer ball. Yeah. So if you actually, yeah, so you can definitely like, that's why it hurts to kick an object, because right, the soccer ball is exerting a force on you. A magnet on a magnet. So the two magnets are exerting a forces on each other, and the forces are equal and opposite in magnitude. So it's a great one. Jumping off of a box, yeah. So if you're jumping, you're pushing off of the box. You're jumping on a diving board. If you're flipping around in a pool, right, you have to basically push on something to get, and that object will push back on you. And flinging a hairband at Mr. Who, yeah. So when you pull back on the hairband, right, it'll release and hit me in the face. So those are all some really good examples of Newton's third law. So yeah, these things are really common in nature, and they're very crucial for how it works. And that's exactly how the force of gravity works. The force of gravity is also an action-reaction force. When an object pushes on you, you are also pushing back on the object. Oh, when the object pulls on you via gravity, the object is also being pulled by you. So even though the Earth and you are both exerting the same force on each other, because they're both action-reaction forces, as you can tell, you are the one that moves, and the Earth is the one that doesn't move. So why is the Earth not moving? Because that doesn't really seem equal and opposite, right? The forces are the same, but somehow the Earth isn't moving. So that's because the reason why is because when we're looking at forces acting on an object, the amount of force acting on an object is going to equal its mass times its acceleration. So F equals ma. That's a very important. This is a very important equation. One of the cornerstones of physics is actually this equation, F equals ma. So right, basically, if I have if I'm applying a force on an object, right, with a certain mass, it'll have a certain amount of acceleration. The way this relationship works, though, is that, right, if I have the same amount of force on an object, the less mass it has, the more acceleration it has. And vice versa, the more massive it is, the less acceleration it has. So for the warm-up, right, as we noticed, the motorcycle had the least amount of mass and it had the highest acceleration, whereas on the opposite side, the private jet had the most amount of mass and had one of the worst accelerations. So there's definitely an inverse relationship between the two, assuming that we're holding the force constant. Another thing that someone also pointed out was that the lighter a mass, the less mass an object has, the less force you need to move it, which is also a really good example, because if if I have a semi truck, right, it's going to require a lot more force to get that going than it is to get like a motorcycle going. So very important equation, but what I also want you to do is I also want you to understand the relationship between these quantities. What happens if I have a more massive object? What happens if I have a less massive object? How does the accelerations vary with these different objects? So yeah. So what I want you to do is I want you to use the force of gravity. So we calculated the force of gravity last time, which I believe it was 734, I think, if I remember correctly. So the force of gravity we calculated last time was 734 newtons. So what I want you to do is I want you to use the previous equation, F equals ma, and I want you to try to calculate the acceleration that you experience and then the acceleration that the Earth experience using the same force. And I want you to notice the difference between the two accelerations. So calculate how much acceleration that you experience, and then calculate how much acceleration the Earth experiences. And I want you to see if you notice something about the two accelerations. So I'm going to give you a few minutes, and let's see if we can calculate. We can use this equation to calculate how much acceleration both you and the Earth are experiencing using this equation and using the force of gravity we calculated earlier, Ft. Okay, so let's calculate how much acceleration we experience and how much acceleration the Earth experiences. So the equation we're going to use is the force on any object is its mass times the acceleration. And we're going to use this to try to figure out how much acceleration we and the Earth experience. So we exert a force of gravity, 4 newtons. This is also how much the force of gravity the Earth is exerting on us. So it's the same force for either one. But for the first case, for us, we're looking at a mass of 35 kilograms. So the force of the Earth, so the force that we are experiencing from the Earth is 734. Our mass is 75. And so our acceleration, we're trying to find our acceleration. So we're just plugging in the force of gravity, which we have, the mass, which we have. This equation. So to solve this, we just divide both sides by 75. We got to cancel out the 75. And so what we get is our acceleration is 9.8. So notice here how this 9.8 is very similar to the value we used, which is 10. So previously what we did is we said that G was 10, and that's actually where this comes from. So this G is actually a measurement of the acceleration due to gravity that you experience. And so we actually calculate it by this. We just use 10 just because 10 is a little bit more of a round number. It's easier to work with, but the more correct value is 9.8. But that's where the 10 comes from. Now, to find out how much acceleration the Earth experiences, we do the exact same thing, but for the Earth, it's going to be much bigger. I think it's 5.97. So the setup is the same, right? So we have the force of gravity is equal to the mass of the acceleration. The Earth experiences the same force of gravity as us. Before. The mass of the Earth is 5.97. So it's much more massive. So in order to figure this out, what we do is we got to divide both sides by 5.97, the 24th. And we get that our answer is something like 1.22 times 10 to the negative 22. So if you don't know what this means, it means that this is what it should look like. It means the Earth is moving this week. So this week will be 22 zeros total. And then it'll move 1.22. So basically the Earth is technically accelerating towards us, but it's so small that you can basically assume that it's zero. So basically the Earth does not move when that's why the Earth doesn't appear to move because it's so much more massive than us. Whereas we move quite a bit. We accelerate at 10 meters per second squared. So that's sort of how you can use that to figure out the acceleration is due to gravity. So what I want you to do now, this is going to be a more complex one. So what we're trying to do here is we're trying to try to derive the equation for the centripetal force. So we're going to use the equations of centripetal force and the gravitational force to derive an equation for the velocity of an object orbiting around another object. So basically what we have is we have two equations. We have the equation centripetal force is mv squared over r. And the gravitational force is gm over r squared. So what I want you to do is I want you to try to derive an equation for the velocity of an object orbiting another object. So basically in this particular scenario, right, there is a centripetal force of this acting on this object, and the centripetal force is pulling it toward the middle of the circle. And the force that's causing it to be pulled is the force of gravity. So using the centripetal force and the force of gravity, I want you to try to come up with an equation for the velocity of an object orbiting another object. So this will be kind of tricky. You have two equations to work with. and try to derive this equation here. Yeah. So one important piece of information that you'll need um, is that the force that's causing the centripetal force is the force of gravity. So basically, the centripetal force is the force of gravity. So you're going to want to use the two, and you're going to try to come up with an equation for the velocity of an object using this starting point. Okay, so I'm going to move on from here. This is actually a very important derivation that's going to be on the main assessment for this unit. So you didn't finish it now, well, you'll get plenty of time to do it later. But I won't do it because that'll defeat the purpose of it. So what instead I want to talk about now is we're going to start talking about revolutions. The whole point of this is talking about orbits. So why do we care so much about forces and stuff? So what we want to do now is we actually want to figure out how do we measure the revolution of an object. What does it mean to revolve around an object? So a revolution means that an object is orbiting around another object essentially, and the revolution time is basically how long it takes to make one complete orbit. So when we actually, what the word year actually means is a year is actually a measurement of how long it takes for the Earth to complete one orbit around the sun. And this is actually 365.24 days. So it takes 365 days for the Earth to orbit around the sun once. So, but that's not the only way we can measure orbits. We can also measure how long it takes for a clock to complete one revolution. We can also take how long it takes for a merry-go-round to complete a revolution. So the question is, how can we measure the revolution time of any object? And I want you to see if you can come up with an explanation. So can we measure the revolution time of an object? Um, so I'm going to put you in your groups and let's see if you can come up with an explanation as to how you might do so. Because Okay, so in terms of measuring a revolution time of things, it actually is very similar to measuring the linear time of distance. So, for example, right, if I'm measuring the how fast you rotate is essentially measuring how fast um, you are going in a circle. So it's very similar to measuring your speed on a straight line. Um, so, for example, if I was measuring how long it took to travel a certain distance d at a certain speed, what I can say is that the time it takes is the amount of distance I'd travel at over the amount of speed. So that is actually very similar to how you would measure how fast something rotates, which we'll do on Thursday. We'll start looking at rotations and we'll start looking at how that affects planetary orbits. But other than that, I think that should be it for today. I don't really have anything else planned. We finished a little early. So if you don't have any other questions, you're free to go on Zoom. Uh, you're free to go on Zoom, and then I'll see you guys on Thursday. Sure.
Thank you. Bye.
Thank you. Bye.
Later, Mr. Who. Later, Mr. Who.
All right, see you, George. See you, Miguel.
Mr. Who? Mr. Who? I think your mic is on me, or can you hear me? Mr. Who? Mr. Who? Anderson, can you hear me?